Hello everyone, greetings from Waterloo. First of all, my co-authors and I would like to thank the organizers for giving us this opportunity to present our paper. So today I'll describe algorithms that reduce the CNOT count for Clifford+T circuits on NISQ architectures. This work has been co-authored with Vlad Gheorghiu from IQC University of Waterloo, Sarah Meng from Dalhousie University, and Michele Mosca from IQC University of Waterloo. This is the brief overview of my talk today. First, I'll introduce and try to motivate this problem. Then I'll briefly talk about some essential preliminaries. After that, I'll describe our algorithms. First, let us understand what a quantum compiler does. Very roughly, it takes a quantum algorithm and outputs a quantum circuit. This consists of quantum gates, which are admissible by hardware constraints. These quantum gates usually belong to a universal fault-tolerant gate set. For example, the Clifford+T is one such very popular gate set. This consists of the following single qubit gates: X, Y, Z, Hadamard, T, phase gates, and their inverses. And it has only one 2-qubit operation, the CNOT. One of the constraints which is imposed by the underlying hardware is the connectivity constraint, by which 2-qubit operations are possible only among certain pairs of physical qubits. This is usually captured by a connectivity graph. There is a permutation which maps the vertices to the qubits. If there exists an edge between vertex I and j, then we say like 2-qubit operations are possible between qubits pi I and pi j. These are the connectivity graphs of some of the architectures that we have considered: Riga 16Q Aspen, IBM QX5, QTX20, 16-qubit square. One solution to this problem is to use swap gates, by which it is possible to move a pair of logical qubits to admissible physical positions. For example, suppose this is our connectivity graph and we want a CNOT operation between qubit 1 and 9. Assume that we have a trivial mapping, that each vertex, like the first vertex, is mapped to qubit 1 and so on. So here we do not have an edge between 1 and 9, but we do have a path. So we place swap gates along this path and then perform the CNOT operation. So one such placement of swap gates has been shown in the circuit, which is to your right. Each swap gate can be implemented using 3 CNOT gates, and each CNOT gate introduces additional noise in the circuit. So now the question is, can we reduce the CNOT count while respecting the connectivity constraints? In recent years, 2 approaches have been used. One uses Steiner trees and the other uses syndrome decoding problem. All these algorithms, however, they act on circuits with restricted gate set. We follow the Steiner tree approach. So what is a Steiner tree? Given a graph with a weight function and a subset S of the vertices, a Steiner tree is a minimum weight tree that is a subgraph of this graph, such that S is a subset of the vertices of this tree. For example, in this graph, I have highlighted this set S, which we call the set of terminal nodes, in red. This is the Steiner tree. All those nodes which are not Steiner nodes but belong which are not terminal nodes but belong to the Steiner tree, they are called Steiner nodes. Computing Steiner trees is NP hard, but there exists efficient heuristics which compute approximate Steiner trees. We have used such efficient heuristic algorithms. Now, there are various ways to represent a circuit. One such way is to use polynomials. This is what we call the circuit polynomial correspondence, by which we associate a phase polynomial and a linear Boolean transformation with every quantum circuit over the Clifford+T gate set. This is derived as follows. First, we initialized each qubit with path variables. The phase polynomial, we represent it as a set of monomials and their coefficients. This is initialized to an empty set. Then for each gate, we change the parity of each qubit according to some rules. Then if that gate changes the phase of the state of the qubit, then we add appropriate coefficient and parity terms to the phase polynomial. For example, consider the circuit which is shown. So now if the X gate acts, we know like it flips the state of the qubit. So the parity changes to 1s or X1, nothing gets added to the phase polynomial. If a phase gate acts, then we add 2x1 dash to the phase polynomial. Here x1 dash is equal to 1s or x1, that is the state of the qubit before the phase polynomial acts. This is essential in order to track where the phase polynomial acts in the circuit. And 2 is the coefficient, like it's a multiple of the pi by 8 term, like the phase term which gets added to the phase of the qubit, like the state of the qubit. Now, when the S dagger gate acts, we add 6x2. When the CNOT gate acts, we know like in the target qubit, the state becomes the state of the control plus the target. So this is how the parities change. When a T gate acts, we add 1, and 1s are x1, like the state of the qubit before the T gate acts. Now here we see like there are 2 such pairs which has the same parity term. This is like the monomial. So we add their coefficients modulo 8. Now when a T dagger gate acts, we add 7, and 1s are x1s are x2. This is the state of the qubit before the T dagger gate. When a Z gate acts, we add this term to the phase polynomial. Again, we can combine 2 such terms. When a Hadamard gate acts, we know like the state of the qubit changes as a superposition of some states. So what we do is we introduce a new path variable x3 and replace the function which was before the Hadamard gate acted. So now the unitary implemented by this circuit can be represented in the sum over path forms, which is shown here. If we have a circuit which does not have the Hadamard gate, then there is a one-to-one correspondence between the circuit and the sum over paths form. But if we have a circuit which has the Hadamard gate, then it is possible to derive a sum over paths form from the circuit. But given one such expression, not necessarily we can have a circuit out of it. So now I describe our algorithms. The basic intuition of our algorithm is to slice the circuit and resynthesize the subcircuits. So we slice the input circuit and get subcircuits. These subcircuits do not contain the Hadamard gate, and then we resynthesize these subcircuits. We have investigated 2 ways of slicing the circuits. In the first method, we partition the gates of the input circuit based on the locality of the Hadamard gates. For example, this is a circuit. There are 2 Hadamard gates. So we partition the circuit as follows. Now we calculate the phase polynomial and linear transformation of each such subcircuit. And as I have explained before, since these subcircuits do not contain the Hadamard gate, so from this description, we can resynthesize the circuits. In the second method, we calculate the phase polynomial of the input circuit. So this is a circuit. And then we partition the parity terms in phase polynomial according to the scope of the variables between Hadamard gates. So we know right after every Hadamard gate, we introduce a new variable. So some variables get lost. So that's why we can synthesize only those circuits which correspond to the monomials that can be written as a function of these variables. We calculate the linear transformation between the consecutive Hadamard gates because these information are essential in order to resynthesize the circuit. So now let's look at a phase polynomial network synthesis algorithm. First, what is a phase polynomial network? So given a phase polynomial set, which I have described before, a phase polynomial network is an n-qubit circuit over CNOT x, t, or any rotation gates, such that for each element, CF, like each such monomial and the coefficients. So this monomial is the parity term, as I said before. The parity F appears before a gate in this set, T, T dagger, S, S dagger, Z, Y. For example, consider this phase polynomial. So this can be represented in the form of a matrix where each column represents one such term, like one such pair. The second last row, this is the bit flip term, like these ones, and the last row are the coefficients. Now, if we do not consider the last 2 rows, then we get a parity matrix. So we now try to synthesize this parity matrix. It is easy to synthesize the bit flip terms. We can simply add X gates. We apply sequence of CNOTs equivalent to XOR operation on rows of P such that each column has only 1, 1. So we do a reverse engineering kind of a thing. So when a column has only 1, 1, then it implies that the corresponding parity has been realized. Then we place a gate depending upon the coefficient of that parity term. So I told before like that parity term was essential in order to track the location of the gate in the circuit. First, what we do is we identify the row J which has the maximum number of ones or zeros. Then we divide the columns into two sets. A one cofactor, these are the columns which has a one in that row, say row J, and zero cofactor, these are the columns which has zero in that row. This row J becomes the pivot row for the columns in the one cofactor. We recurse this procedure on the zero cofactor columns. And we continue doing this till each column has been assigned a pivot row. For example, consider this matrix. So first we pivot on row I1, we divide into the zero cofactor and one cofactor. Then we pivot on I2 for the columns in the zero cofactor. We again divide into zero and one cofactor. Then we pivot on I3 and we again divide into zero and one cofactors and so on. Now for each set, we check if there are any other all one rows, else we subdivide further. For example, we see like for this set, there are other rows which has all one in these columns. Now, given the connectivity graph, in that graph, we find a Steiner tree rooted at I3, the pivot row with terminals I3, I4, I5, I6. Then we apply a sequence of CNOTs depending upon traversals in the tree such that the parity at I3 is the XOR of the parities of at these nodes like xi3s or xi4s or xi5s or xi6. And we sort the rows in V such that the ones in these rows, I4, I5, I6, they get cancelled. Now to apply the sequence of CNOTs, we have developed some procedures. So we call this A. So suppose given a tree which has root R and leaves are L1, L2, L3. These are the parities at these nodes. Then there exists a sequence of CNOTs depending on tree traversals such that the parity at the leaves is the parity at the roots or the parity at the leaf. And the parities at the Steiner nodes remain unchanged. So consider the Steiner tree, which we had from our parity matrix. So our root is at 3, which was the pivot row. We separate this tree into subtrees. Like we do a depth first traversal of this tree. We start from the root. Whenever we reach a terminal, we stop. We make that terminal the root of the next subtree. We again traverse depth first and stop at the next terminal and so on. For example, here, suppose we have 3 such subtrees. And these are the parities at the nodes, like the terminal nodes. We flip each subtree, and then we apply A starting from the last subtree. So this is how the parities change at the leaf, that node 5. And we apply this row operation, like we add row 5 to row 6. What it does is it flips the ones at row 6. We do the same kind of a procedure for the second subtree. We apply the similar kind of row operations, and similarly for the first subtree. After all these row operations, we find that we have flipped all the ones in these rows. So after applying the phase polynomial network synthesis algorithm, so we saw like these things got flipped and the parities got realized. So we have a circuit. Now we implement this circuit. So now the parities of these qubits change accordingly. So we have a transformation that maps these states to these states, y1 to yn. But we require a transformation that actually maps this y1 to yn to x1 dash to xn dash, because these are the parities which we want. So this is a linear transformation, and this can be realized by a circuit on CNOT and X gates. So now let us look at a linear transformation synthesis algorithm. A linear transformation matrix is a n cross n plus 1 augmented matrix. The rows are indexed by qubits. The first n columns represent initial path variables x1 to xn. The last column indicates bit flips. Now, given a linear transformation matrix, we apply some row operations which correspond to applying CNOT such that A is reduced to identity. We again follow reverse engineering idea somewhat similar to Gaussian elimination. First, we look at the last column. If there is a 1, we flip it. We apply an X gate to that row. Then we apply a series of row operations such that A is reduced to an upper triangular form. We transpose this matrix and then again apply a series of row operations such that A dash is reduced to identity. Each such row operation corresponds to the application of CNOT gates. Now, I have said before that we use such a subroutine A such that We apply a sequence of CNOT gates depending on tree traversals, and the parities at the leaves change as follows, and the parities at the Steiner nodes, they remain unchanged. Now we have designed another subroutine by which we can apply a sequence of CNOTs depending on tree traversals such that this time the parity at leaf becomes the XOR of the parities of all the nodes which are between the root and the leaf, and the parities at the Steiner nodes, they remain unchanged. Now let us look at the method by which we reduce the matrix to an upper triangular form. So we are given the linear transformation matrix and a connectivity graph. We do the following, starting from the leftmost column. If there is no 1 in the diagonal, then what we do is we apply CNOTs to propagate 1 from a lower row. Suppose S is the set of rows below the diagonal which has a 1. Then we construct a Steiner tree on this connectivity graph, restricted on those vertices which do not include 1 to I minus 1. Here we have assumed a trivial mapping from the vertices to the qubits. That is, vertex 1 maps to qubit 1 and so on. This Steiner tree is rooted at I and has terminals as S, like all those rows which has a 1 below the diagonal. We separate this tree into subtrees and apply A dash. We apply the corresponding row operations on A. We say a column is reduced if all the rows below the diagonal has 0. For example, consider this linear transformation matrix. I'll show the reduction for one such column. So we start with the first column. So here we have 1 at row 2, 6, and 7. So we build the following Steiner tree rooted at 1 and terminals as 2, 6, 7, and 1. We separate it into subtrees in a similar fashion as I've described before, like from one terminal to the next terminal. So here we get 2 subtrees, and these are the parities at the various nodes of these subtrees, like especially the terminals. We apply A dash starting from the last subtree. This is how the parity at 6 changes after we apply this A dash to T2. We do the following row operations by which we can flip the 1 at row 6. We apply A dash to the first subtree. This is how the parities change. And we do similar row operations. So after this, below the diagonal, all the rows have a 0. So we say like column 1 has been reduced. Now, while reducing to identity, we do the following. So now we have transposed the matrix. So now all the zeros are in our upper triangle, and we want to reduce the lower triangle. So we follow almost the same procedure as in upper triangular form, but this time we remember like there are zeros in the upper triangle, the now upper triangle, which we do not want to disturb. So this time we want the parities at each non-diagonal node to be xj dash or xk dash, where j is the non-diagonal node. And we want k to be less than j. Xj dash, xk dash are the parities at node j and k respectively before the transpose step. So this is to ensure that we do not disturb the all zero upper triangle. And this time we apply A instead of A dash. If k is greater than j, then we apply some correction procedure. So I'll show you the correction procedure. For example, suppose we have 3 subtrees, and after applying A from the last subtree, this is how the parities change. Like these are the parities accumulated at the various nodes. Now we see at T3, the parity at 2 is x2s or x7, and 7 is a higher index. We do not want it. It might disturb the zeros. So we do the following. We find the shortest path from 7 to 2, and we apply A. So this time the shortest path is the subtree itself. So the parity at 7 initially was x7s or x3, and at 2 it was x2s or x7. So after applying A, the parity at 2 becomes x2s or x3. It's still now not correct. So now we find the shortest path from 3 to 2. So this is the path obtained. So initially the parity at 3 was 3s or 1, and at 2 it was 2s or 3. So we apply A, and the parity at 2 becomes x2s or x1. Now it is correct. So after doing these procedures, we get a sequence of gates, and we place them in the circuit in the following way. Suppose X is the set of X gates obtained, YU is the sequence of CNOT gates obtained while reducing to upper triangular form, YL is the sequence of CNOT gates obtained while reducing to identity, YL dash is the same sequence as YL with control and target flip, because we should remember we transposed the matrix. Then we place the CNOT gates as follows and the X gates as follows. YL dash followed by the reverse sequence of YU and then the X gates. Now I'll describe the subroutines A and A dash, which we have used so crucially. So for A, we want a sequence of CNOT gates such that the parity at leaf becomes the leaves or root. Okay, so here we want X5s or X1. So this is the root and this is the leaf. Every other parity should remain unchanged. So we do the following procedures. First, we do a bottom-up traversal. This means we start from the leaf and we traverse the tree towards the root. And we apply the CNOT as follows. Then the parity at these nodes change as shown in the figure. So we do it, continue doing it like that. And we traverse till the second node, like the node which follows the root. Then we start from the root and traverse towards the leaf. So we do a top-down operation. We again place the CNOT as follows. So here we should remember that the first index is the control, the second index is the target. And the parities change as follows. So this time we see like the parity at leaf becomes X1s or X5 as we wanted. Now we want to correct the parity at the Steiner nodes. So we again do a traversal, this time from the second last node towards the root. So we place the CNOTs and the parities change as follows. Again, we start traversing from the second node towards the second last node. We again place the CNOTs and the parities of the Steiner nodes, they now become correct, like the parities which were before A was applied. In A dash, we simply skip some steps because we do not want to have some CNOTs which are not really necessary. So suppose it is the same tree, and we this time want the CNOT such that the parity at leaf is the XOR of the parities of every node in which are between the root and the leaf. And all other and the parity at the Steiner nodes remain unchanged. So this time, first we start from the root, traverse towards the leaf, we apply the CNOT as shown and the parities change as shown. Then we start from the second last node and traverse towards the leaf. We place the CNOTs and the parities change as shown. So now I'll give some comparison of our algorithm with the previous algorithms which used Steiner trees. One was given by Kissinger and Degreen, another was given by Nash, Gheorghiu, and Mosca. Let's look at the linear transformation synthesis part. While reducing to upper triangular form, we traverse its Steiner tree twice using A dash, while both NGM20, KDG20 traverse it 4 times. While reducing to identity, NGM20 uses templates and KDG20 uses a different kind of a recursion. The way we do our correction ensures that we get less number of CNOT gates. Now the phase polynomial network synthesis part. The way we flip the Steiner trees and drew the traversals, it ensures that all the parities are realized correctly. The phase polynomial network synthesis algorithm, and which is described in NGM20 as it is described, it does not realize all parities in the circuit, so it is not correct. KDG20 hint Steiner trees can be used, but they do not explain how. Now for circuits which include Hadamard gate, NGM20 sketch how to use their phase polynomial network synthesis algorithm, but it itself is not correct. However, our way of partitioning or slicing the circuits are quite different. We implemented our algorithms on some benchmark as well as some random circuits. These are the results. So these are the architectures we have considered. The second column is the number of qubits of the circuit. These are some of the benchmark circuits. So in the fourth column, we have given the overhead if we would have used swap template. For example, we would have used swap gates, converted them to CNOT gates, then did some optimization, then we would have had this kind of an overhead. CNOT opt A is the name of our algorithm as it is in our paper, which uses the first kind of slicing, and CNOT opt B uses the second kind of slicing. These are the overheads we have. In some cases, it reduces because it's possible to do some optimizations. These are the results on some random circuits. So in the third column, we gave the initial number of CNOT gates. Like while synthesizing these random circuits, these were the initial number of CNOTs in those circuits. So this is the overhead which we get after if we use the swap template, and these are the overheads which we get if we used our 2 kinds of algorithms. So here we see, like if we use the first kind of slicing, then we get considerably less overhead. Not only that, Our scaling is also very nice in the sense that if we increase the number of CNOT gates, so like if the circuit size increases, the overhead doesn't blow up. So all our circuits, like, and each row here actually gives the average statistics of 10 circuits. And if you look at the time required to implement these things, that is also quite reasonable, it's quite less. So to summarize my talk, we have developed algorithms to reduce CNOT count while implementing Clifford+T circuits on connectivity constraint architectures. We have used slice and build techniques. We have used Steiner trees to resynthesize phase network circuits and linear transformation circuits. We have obtained significant reduction compared to swap template. And also our algorithm has nice scalability. Thank you.